One of the most important things to know when we talk about making a building thermally insulated, well insulated, to keep heat transfer through the wall to a minimum, and that can be the heat that you want to retain in the room if you're heating the space, or the heat that you want to keep out if you're cooling the space. And all of that is primarily calculated with this idea of the resistance, the R value of the walls and the roofs and the floors that we construct. So here's a graphic of this idea of R values. In this case, this is um, some type of probably a foam insulation or a fiberglass insulation. And the idea that typically they all have a thermal conductivity to them when given over a certain thickness of material gives you a certain kind of stacked up resistance in R value. So typically, if you double the thickness of a material, you kind of double its R value. And that's not always a linear calculation. But this is the idea of insulating roof trusses or roof rafters in a home, and the idea of R12 being just filling the pockets with 4 inches, and then going up to R49, which is filling them up with something that would well exceed the depth of the joists themselves. So, but this idea of R value we'll find in all of our building components. And here's an example of an R value, a stack up of wall components from inside to outside. And I'm showing you this because it's not a standard wall. It isn't a stud wall with insulation in it, but it is just a built up of, well, in this case, laminated timber, wood fiber insulation. So this idea of R value in a wall can be any kind of componentry that we're building out of. And the nice thing about R values is they can be summed together. So for the total R value, the total resistance to a wall, it's the sum of all the individual resistances. Now, there's one other way that we look at measuring the heat loss through a wall, and that's the U value, which is just the reciprocal of the R value. And the problem with U values using them is that they really can't be added together because they are the reciprocal of the sum of the R values. So you don't add U values together, you add R values together to come up with total resistance. But in this case, we're going to deal in our lab and through most of practice with the idea of using R values. U values come into significance when we talk about Windows systems many times. So as I just said, this idea of R values is an additive process. So we have, in this case, the total resistance of the wall, and these are just some various kinds of similar representations of these graphics that I pulled off the internet. Um, the R value is R1 plus R2 plus R3 plus R4 gives you a total R value through the wall. The neat thing about these two graphics is this idea of the temperature profile going through the wall. So in this case, this is a glass enclosure. So we have the R value of the glass. We have the R value of the air between the glass, and that is actually, air is a very good insulator, so that's not trivial. And then the insulating value of the other layer of glass. In this case, it's being a double layer of glass. And what we can see is this idea of a higher temperature, let's say outside, and a lower temperature inside, maybe we're air conditioning, and the idea of the thermal profile changing as we move through the material. Now, this may not seem important at first, but one of the issues that will come up is that if the temperature drops too low inside of a cavity and or space within a wall enclosure, condensation may occur. In this case, if this is probably a well-built window system, so there wouldn't be any moisture in here. But if there was moisture in here, a gas film, a vapor film could form on the glass layer if this temperature profile was too steep and there's too much relative moisture available. And if that was an interior wall of a building and you couldn't see it, but moisture was condensing inside, that could become very problematic with creating mold and mildew inside of the system. So I want you to keep in mind this idea of a temperature profile as you go through the wall, and the idea that at some point you get to a temperature which may be so low as to be the dew point of the air that's inside of that cavity. And we talk about moisture barriers and air barriers later on in the course, and it'll come up again. I use these references here about describing these kind of cross sections of walls or cross sections of glass. And maybe I wasn't very clear as what I was showing you here. But inside of Revit, our BIM modeler, we can also do the same thing with the way we build up walls. So in this case, I've just grabbed a screenshot of a wall system that we built up with the idea of plywood, um, wood framing structure. This is 5.5 inches of stud thickness, an air gap, maybe a gypsum board material applied to it, some insulation inserted in it, and all of these can be summed together to give a total R value for the wall system. And in our BIM modeler, that can be automatically calculated by adding these specific materials because the software knows the resistance value of these materials. It can calculate a total R value by adding them together, and that's just what is represented up here at the top. So we have many tools to kind of automate this process of calculating the amount of resistance a wall that we build will have. So once again, this idea, I want to also bring up this idea of R value and U value, and they're really reciprocals of each other. So something with a high R value will have a really low U value, and that's a good thing. Um, and it'll probably, U values will only come up in conversation when we're talking about glazing systems. We're going to look at creating a building envelope and talking about heat loss. And our primary way we look at heat loss is that idea of R value, the transfer of heat through wall surfaces. But we really need to step back and look at this idea of the total building envelope, and that there are many other ways for air to get in, or excuse me, heat to transfer in and out of a building. And one of them is through what's called infiltration, air infiltration. Just a natural movement of air from outside to inside through cracks, crevices, openings, ventilation systems, gaps in construction. And in recent decades, it's been really quite a strong move to make buildings more and more airtight and to cut down on that air infiltration because we don't want to heat air that we haven't desired to have in the space. But with that comes a downside, and that is that tight buildings don't breathe fresh air. We need fresh air, so we need to exchange the heat exchange the air from the outside to the inside, and minimize the amount of heat that we transfer in that exchange. And we'll go through that a lot more in some future courses, or excuse me, future modules when we talk about wall construction techniques and where we place the idea of moisture and water barriers and how we ventilate with heat exchangers. So we'll break there and pick it up on the next section.